So thank you all for joining this Applied PDE seminar at the University of Washington. Our speaker today is Beatrice Pelloni from Heriot-Watt University. Beatrice is originally from Italy. After leaving Italy, she did her PhD at Yale University before spending time as a postdoctoral fellow at Imperial and then as a faculty member at Reading. She's been at Heriot-Watt since 2016. She's been distinguished by the Olga Taussky-Todd Prize Lecture and by a IMA fellowship. And today she's going to tell us about time periodic linear boundary value problems on an interval. Thank you, Beatrice.
Thank you very much, Bernard, and thank you for the invitation. This is sort of second best because really Bernard was kind enough to invite me to come and spend some time and give a colloquium. And I really want to do that. I hope the plan is that I'll do that next year, but this year traveling was still very difficult because I'm in my last stretch of really the last weeks of being head of school, and over the pandemic, this has been a hell of a job. And I could not come for long enough to make it worthwhile to trek all the way from Edinburgh to Seattle. But I've been once only to Seattle and I do want to come back. So I will. And thank you, Bernard, for giving me the opportunity anyway to speak today. As I said, being head, it means that most of the work I've done recently has been either with my students or, as in the case of what I'm going to talk about today, with very solid collaborators and former students. David is my former PhD student, and it's on somehow is in my comfort zone, stuff that I've worked on for a long time, and also is relatively simple. However, I think there are a couple of pretty cute ideas that open up the problem entirely. And so although it's relatively simple, I hope it will be clear and be interesting. So what is the problem? So just mathematically, the problem is very simply stated. You have a dispersive PDE posed on a finite interval, and my interval will always be 0, 1, which is slightly misleading because you never see the 1 in anywhere, but the 1 is there. If I had capital L or any other length, the length plays a role, so I will indicate where that happens, but I didn't want too many constants floating about, so I'll stick with 0, 1. And you're given time periodic boundary conditions at the two ends of this intervals of 1D. And the question that you may ask is, does it follow that the solution is time periodic, either exactly or asymptotically, with the same period? Well, if it is periodic, you would expect that it would have the same period as the boundary condition. I'm assuming that the period of the two boundary condition is the same. This is really not important, but then there is only one period around, and it's natural to expect that that's the period that appears, if any does. And these are the three standard examples for linear PDEs of dispersive type that one looks at. The two second order and the third order, all the plethora of possible behaviors is covered by looking at these examples asymptotically. This is, you could have lower order terms and it wouldn't change very much. You could go higher order, but again, it would just repeat what all the possible behaviors are captured by these examples. Sometimes I'll call it the first equation linear Schrodinger, sometimes free Schrodinger, both I always mean the same. There is some experimental interest or evidence for these kind of things. Of course, these will not be really linear problems, but Jerry Bona told me about this a long, long time ago. He was interested in proving rigorously that if you look at waves in a shallow tank or canal, if you have a channel where you can produce shallow waves like we do have near Heriot-Watt. We had the canal between Edinburgh and Glasgow where the first solitons were observed. It's just about half a mile from my office, which is quite exciting for an integrable system person. But anyway, if you have even an experimental setup with a tank, it's old experiments going back to Zabusky and Galvin that if you have a periodic wave maker at one end and somehow stop measuring before there is reflection from the other end, it seems that the solution becomes periodic with the same period as the wave maker. And even in the linear regime, there was no result. So even if you approximate this problem with just the Stokes equation, for example, rather than the full nonlinear KdV or any of the equations in that class, there were no results until relatively recently. And the first results in around 2008, 2010 approximately, were on the half line, because the half-line problem is easier than the full line problem, than the finite interval problem, assuming that you have vanishing condition at infinity, and that was what was looked at. So let me just say what exists. As far as I know, this is the sum total of the existing results. All the results that I'm listing on this page are for problems on the half line. And as I said, Jerry Bona really pushed Thanasis Focus to look at the problem once he had this, he and I had analyzed the Stokes equation with the unified transform approach, and there was a nice and neat representation for the solution of the half line problem. They looked at, they just did an asymptotic analysis of it. It's not very difficult once you have that setup to prove that indeed, if you start with a time periodic boundary condition at 0 and 0 initial condition, so it was a Dirichlet boundary value problem with 0 condition and only this, not in more generality, then you can prove that the solution will be will become asymptotic for a long time. They also sort of did say something about the nonlinear regime, but didn't prove anything in that original paper. The first result for the nonlinear, for nonlinear equations were by not very long after by Boutet de Monvel, Kotlerov, and Shepelsky. And again, they looked at one specific example of a time periodic boundary value problems and proved that if you have this, but just a single oscillator exponential as your boundary condition, then as your Dirichlet boundary condition, then the Neumann datum also will have asymptotically the same form with a different constant. And then in 2015 or 14, maybe Focus and Lenels looked again at NLS on the half line, and they had also an earlier paper that sort of extended a bit the results of Boutet de Monvel and the others. But this paper in 2014 has a slightly different approach. It's very perturbative. It assumes an expansion for the solution with regards to a small parameter, and then assumes that if you have a periodic Dirichlet datum, then the Neumann datum is also periodic, and gives a constructive way to build the coefficients for the unknown boundary value perturbatively. But in principle, to all order, in some cases you can sum this series and then it's fully explicit. And in the course of doing this, they introduced something that they call the Q equation. And I will return to this. And in last year only, Bona went back to this problem, which had been one of the things he wanted to do. He was on his bucket list, so he finally did it and extended this result to KdV in a similar way, the result of Focus and Lenels. Again, though, only the Dirichlet problem with 0 boundary condition, with 0 initial condition. So starting at rest with a time periodic forcing at one end. Around 2010, there was also a paper by Dujardin, and this is the only paper I know of that looks at the problem on a finite interval. And in some sense, there was a surprise in this paper. It's very hands-on. It looks at the problem and does a lot of very specific analysis of the particular Fourier series representation of the solution, but it proves that again, for a Dirichlet problem with zero initial condition and zero condition at the other end of the interval, then there are conditions that need to be satisfied for the solution to inherit the periodicity of the boundary condition. It's not automatic. In some cases, the solution is not finite. And in fact, gave a series of results on this, and this condition on which is essentially the linear dependence over the rational of two numbers, the period theta of the boundary condition and 2/pi. It's not a difficult paper, but it doesn't quite, it's not very revealing in as why this is the case. And also it doesn't discuss the fact that this happens for the NLS, whereas it contrasts with the experiments. If one thinks of a linearized case of KDV, and instead uses Stokes, it seems that the solution inherits the periodicity. The same is true for the heat equation. So there is clearly a different behavior, but it's not clear from the paper why and what is the mechanism that drives it. Okay, so why did we look at this problem? Well, we look at this problem because the problem was suggested to me and Dave by Tanasi, and we worked on it and discovered that there was something interesting to say, so we pursued it. And what Tanasi did with one of his PhD students was taking this idea of the Q equation and go back to the linear problem to see what that would give, only on the half-line problem. He did it for the half-line problem. So what is the Q equation? This is a very, very sketchy summary of what the content of this paper of Focas and Lennels is, but essentially they assume that the Dirichlet given datum G0, this is the boundary value at x equals 0, and also the unknown Neumann datum, they assume that they are time periodic. Asymptotically, there will be other decaying factors here, but never mind, of the same period. Omega here is the frequency, the same. And then give a constructive way of building this coefficient Cn from the ANs via a function Q, which is also periodic of the same period, which is essentially the solution of the T part of the Lax pair at x equals 0. And the fact that this function Q, here is QB, but has certain analyticity properties is crucial to ensure that the system that one derives for these coefficients dn and in turn for the coefficients cn is non-singular. So that is the idea. There is some, as usual, when you use this unified transform approach for boundary value problems, analyticity plays an important, crucial role in being able to determine more conditions for the quantities, unknown quantities at hand, from just one equations or one relation. This is a very quick sketch, but this idea was then used by Focas and his PhD student to do a linear version of it, again, to solve problems on the half-line. It turns out that in the linear case, you don't need to sweat too hard. If you look at the T part of the Lax pair at x equals 0, really what Q is just the Fourier transform of the solution, which is an unknown, of course. But what is So it's not, it's there for you in plain sight. But what is important, the important conceptual step, which is not new, but is maybe its use in this context is new, is to think of this spectral Fourier transform not on the real line, but on the complex plane, and use analyticity considerations. This is the name of the game in all of this and it has been for a while. Okay, so Thanasis and Christina had done the half line. Thanasis said, "Oh, would it be interesting to look at the finite interval?" And in fact, none of us remember these results of Dujardin's, though I knew them. I then realized that I didn't know them. And so, in fact, Thanasis expected that it would immediately follow that if you give time periodic boundary conditions, the solution is time periodic, at least asymptotically. Okay. And as I already said, this is not really always the case. So this is an example of an inverse trajectory with the results. The original results are in the nonlinear case, and we're bringing them down to the linear level to see if they give us anything. So what's the outline? This Q equation approach can be used to study the asymptotics of the Dirichlet to Neumann map and to determine whether the solution, what properties the solution itself has. And by using this, so by using the Fourier transform of the solution of the PDE and considering it as a function in the complex spectral plane, one can derive very easily necessary condition for asymptotic periodicity. So there is a set of conditions that have to be required for any periodicity to hold. And this, yields the constraint that Dujardin had found very naturally in about 2 lines, and generally, not just for 0 initial datum and for periodic conditions that can be non-zero at both ends. So it's a more general way to even think of whether or not you need to impose necessary conditions, and it extends to general dispersive problem with a general dispersion equation, higher order, more general boundary condition, whereas all the work that has been published so far really depends on both a special choice of conditions and on having a Fourier series representation for the solution, which, as some of you know, cannot be guaranteed for the 3rd order case. So this approach is more general and can be used on the finite interval. Once you realize where you're going, actually the template of the proof is really simple, and I will then illustrate it in 2 1 second order and 1 3rd order examples. So if you assume, just as Thanasis and Jonathan Lennels have done, assume that everything inside, so your unknown boundary values and the solution are time periodic of a fixed period, then the Q equation, just analyzing this analyticity, gives you the necessary conditions you need to impose to have any hope to derive explicitly the boundary values from the unknown ones from the known ones. And once you assume that these necessary conditions are satisfied, you still have to prove periodicity. And to do that, you need to do something with the representation of the solution, that it's either in series form or in integral form. The general strategy to do this, assuming that you have the necessary conditions in the linear case, but in fact, preparing this talk, I had some ideas about how you could extend this also as an idea to the nonlinear case, but this is working for the future, is to split the solution. And in fact, it's always possible to find a part of the solution U1 corresponding to a special initial condition that it's of a very special form, that guarantees that if you're given tau periodic boundary conditions, the solution is tau periodic, only starting from this particular initial condition that I called U tau. And then what remains will be the solution corresponding to the difference between your original given initial condition and this special u tau, and the homogeneous version of the boundary condition. And this is what you need to prove has some property. It may be periodic, it may be decaying, it may have a superposition of different periods. And the form of this U2 is what really drives what happens. U1 is always periodic of the same period as the boundary condition. U2 depends. If, for example, U2 is also time periodic, but with a different period, then there will be an arithmetic constraint between tau and this other period in order for the sum to be periodic. And this is exactly the particular example that Dujardin had. But this strategy works in general. So let me just illustrate it in a couple of examples, just to show you that it's not, it's a very simple template. It's very powerful though. It's a simple idea. So as I said, for the linear case, the Q equation you can define it through the T part of the linear lax pair evaluated at x equals 0. But once you do that, you realize that really what you have is just the Fourier transform of the solution, the Fourier transform on 0, 1, okay, with a minus. That doesn't matter, minus or no minus. So in particular, it's always an entire function of k. Entire because x is finite. It's only on an interval. And so the Q equation really is just the Fourier transform of the PDE. And this is written here in general for a general PDE whose dispersion relation is given in terms of these coefficients Cj. So for example, just to be concrete, if you look at the free Schrodinger equation, then the Q equation is just given here. G0 and G1 are the values of the boundary values at x equals 0. H0 and H1 are the boundary values at x equals 1. And because this is second order, there's only u and its derivative. And for third order here, you will have u, the derivative, and the second derivative at both 1 and 0 and 1 actually. And of course, this is just the PDE, the Fourier transform of the PDE. It involves all the boundary values of which you only know, for example, maybe if it's a Dirichlet problem for the free Schrodinger, you only know G0 and H0. If it's a Neumann, you only know G1 and H1. You may know a combination, but two boundary conditions. And for the third order problem, you can give one condition at 0 and two at 1, or some coupling conditions. Okay, so you don't know all these functions here. This is just formal. And as you know, there is a whole, that's when the unified transform has a way to derive the unknown boundary values from the known boundary conditions. I'll leave it there. We know how to do that now, but it's not what is important. So how do you derive these necessary conditions for time periodicity? Well, assuming that everything inside is at least asymptotically time periodic, so your boundary values at 0 and at 1 are periodic of the same period, and the solution, or rather its Fourier transform, is periodic of the same period. Let's assume this to begin with. Then if you substitute this ansatz into this equation up here, the Q equation, so the PDE, you get an expression for these coefficients Q, small qn, in terms of the coefficients for the boundary values. And because qn are entire function of k, and there is a denominator here, it's a fraction, it must be that if for a given n there are zeros of this equation, then the numerator has to have a 0 of the same order. And that's it. These are the necessary conditions for periodicity. And let's see a specific case. So you can ignore this. I thought that it would be useful to sketch the problem for the free Schrodinger here. So what I'm having is just a sketch of the problem, and I'm assuming I'm given the Dirichlet boundary condition. So U at one end and at the other, and examples, and a particular example that Dujardin proved and that I'm going to show you as well is, for example, you're given sine pi squared t at one end and 0 at the other, and perhaps a 0 initial condition at the beginning. And so that's an example where there is the only datum that's given is time periodic, and everything else is 0. It's sort of, your first guess would be that U is periodic as well, of the same period, at least eventually. And it turns out not to be the case. So let's specify what these necessary conditions look like for free Schrodinger. So that's the equation for free Schrodinger. Again, Gn 0 are the coefficients of the Dirichlet boundary datum at 0, Gn1 the Neumann boundary datum at 0, Hn0 Dirichlet boundary datum at 1, Hn1 Neumann boundary datum at 1. But this is just the general form of the PDE, gives this by integration by parts. So this is the expression that you derive for these coefficients that would allow you to reconstruct a time periodic solution, at least asymptotically. I will not say asymptotically, everything has possibly a decaying part to it, but it's not affecting any of the proofs, so I will probably not mention it all the time. So we're asking that when k is equal to plus or minus either I square root of n omega or plus or minus n omega when n is negative, that the numerator is 0. So for each of these k's, you have a system of two equations at n and at minus n. And this system, you want to know, you want to solve this system for the unknown boundary conditions. In this case, Gn1 and Hn1, or both at n and minus n. And if you do that, and you just go ahead and solve it, in the case that you have this special boundary condition that I indicated, so G0, the Dirichlet datum at 0 is just this particular periodic condition. The period of this function is 2 over pi, which is sort of H0 is 0 and 0 initial condition. Then the Fourier coefficients in time of small g0 are given here. There's only 2 that are non-zero. And you can solve it immediately. And you see that the coefficients for n equals -1 of the Neumann datum have sine pi at the denominator. So clearly make no sense. Okay, so somehow the assumption that you can expand the Neumann datum as a time periodic function yields a contradiction. Okay, so this is one part. So it's not true that the solution is time periodic. In fact, the solution blows up. And you can do this in general for if you're given any initial condition, any time periodic boundary condition. If you solve the system, you always get something that has this form, and at the coefficients corresponding to negative ends have sine of square root of n omega there, where omega, of course, is the frequency. So it's 2 pi over the period. And so the necessary condition to even hope to have a solution that is periodic is that this number, 2 pi n over tau, is never an integer multiple of pi. Okay, or if it is, that the corresponding Gn numerator is also has a 0 of the same order. I haven't written that there. And this is exactly rewritten, but it's exactly the particular condition that Dujardin had found for the case of 0 initial condition. And the way he did it is by a very careful and relatively long analysis of the specific Fourier series representation. Okay, so now we have necessary conditions. We still haven't proved that actually the solution is periodic. And so we have to still do this. And as I said, to do that, we decompose the solution in two parts. And the first one is a part that is by construction time periodic. And the second will show in this particular example for Dirichlet boundary conditions for free Schrodinger, that U2 is always time periodic of period 2/pi. If here the important number is 1. If the length of the interval was L, this would be 2L/pi. So there is an interplay between the length of the interval on which the problem is posed and the period of the boundary condition. And it follows, since these two things have different periods, that the solution is periodic only if A, the necessary conditions are satisfied, and tau and 2/pi have a common multiple. So they're linearly dependent. So how is this U1 constructed? Well, it's just a reverse construction. You assume that the solution is time periodic. You take the Fourier transform of the solution is time periodic. Take the inverse transform to write the solution itself as a Fourier series in terms of certain coefficients, which I've written here explicitly, but it's just an inverse Fourier transform. And by construction, this function U1 that you have constructed is time periodic of period tau. That's your assumption, and it satisfies the boundary conditions, satisfies the PDE. And what is its initial condition? When it's just the value of this at t equals 0. So let's set that as U tau by uniqueness of the solution. If you choose U tau as your initial condition and look at the PDE with those boundary conditions, that's the only possible solution. So it will be tau periodic. And you can always play this game because we have an explicit way of representing the solution abstractly. And for U2 now, if you're given any initial condition, and I can select, for example, the one, my original one minus U tau, and then homogeneous Dirichlet boundary condition, then I can just, this homogeneous Dirichlet boundary condition for a second order problem, I can write the solution, here it is. And of course, you can see that it's time periodic of period 2π. It just is the fact that I have homogeneous Dirichlet boundary condition. So I'll assign the basis, the eigenvalues of this problem are just πn. So it's time periodic of period 2π. End of story. So if you put all of this together, is that for the case of free Schrodinger with Dirichlet boundary condition, the solution can only be periodic if the necessary conditions are satisfied. And if these two special numbers, one depending on the period at the boundary condition, the other depending on the length of the interval, are linearly dependent. And otherwise, the solution in general is not periodic. It's not bounded, in fact. So this is easy, it's simple, it's very clean though, and it actually gives a template to prove this in general. And so let me show how you would go around doing something similar for the Stokes equation, so just the linear KdV, to show also what is equal and what is different. Okay, so that's the PDE. It's just the linear part of KdV, and I only retain the highest order derivative term. That is just for convenience. You can add ux, and essentially nothing conceptually changes. So if you solve for the coefficients of the Fourier transform of the solution, in this case, that's the expression again, you have a denominator, and to ensure that Q and K are entire functions, you must make sure that the numerator is 0 at any 0 of n omega minus k cube. And these are just the cube roots of reals and their rotations by 2 pi over 3. So Kn are just the unique, I indicate with Kn the unique real cubic root, and then you will have to rotate it by 2 pi over 3 and 4 pi over 3 to get all 3 roots. Okay, so in particular, these roots are aligned, are always either on the real axis or on the two line through the origin, that with the angle 2 pi over 3 and 4 pi over 3 from the origin as you turn. Okay, so you know exactly where these where the problematic points are here. So first example, the sort of what you would the first generalization that you might take is what I would call Dirichlet or Dirichlet type boundary condition, but you have to give 3 boundary conditions for this problem. So it's u at 0 and 1, but also ux at 1. And I'm assuming that u1 and ux at 1 are 0. So this is really the linearized model for the experiment in the tank. You have one periodic wave maker at one end and assume that everything goes to rest at the other end. And then the system to solve is the system that you see here. And the determinant of this is, so for at each of these values, Kn, alpha square Kn, you get, from this, you get 3 equations for each n. And the determinant of this system is given here. And this is work that now is maybe 20 years old or something. We know we know where the zeros of this determinant are. Okay, and let me show you where you are. Let me show you where they are. They're as far away from the black lines where the zeros of the denominator, so the cube roots, lie. So they never coincide with the Kns, which means that this denominator, since we are only evaluating it at Kns, is never 0. So the system is non-singular and you can solve it always in this particular case. And this aligns with the idea, with the experimental results, that if you have a periodic wave maker, the solution does eventually become periodic. And okay, so you don't need any conditions on the period. And again, as before, you can construct the first part of the solution u1 to be exactly of the same period as the boundary condition. And then what's left will solve a problem with a different and generic initial condition, but with homogeneous boundary conditions. How do we analyze the large T behavior of this solution? Well, this problem does not have a series solution. And this was one of the interesting finds of the linear part of the unified transform, and somewhat unexpected, but now well understood. So there's no series solution, but there is an integral representation. And here I've written in a somewhat non-orthodox way, but never mind, you can write it in this way. And z plus and z minus are explicit in terms just of u0 minus u tau and then the determinant, because remember, this is the problem with 0 boundary condition, all 0, so G0 is gone. G0 is only influences only u1. In here, the homogeneity makes this only be dependent on the initial condition, and these E plus are sectors. In fact, these are the sectors where the red dots are. And you can do a standard arguments for these two integrals to compute the large T asymptotics of them, and it turns out that both integrals yield a decaying contribution. So U1 is tau periodic, U2 is decaying. So asymptotically, the solution U overall is tau periodic. So it's periodic with the same period as the boundary condition. No surprises. This is what we were expecting. This is what we get, but in a very straightforward way. It's a little bit less straightforward is the conditions are coupling. So something more like Robin boundary conditions. So for example, you're given again a wave maker at the 0 end, 0 at the 1 end, but then the derivatives are coupled, but with a coupling constant that is not different from 1. That's an important thing. Then again, you have a determinant, and again, this determinant has zeros that are not ever coinciding with the cube roots. Okay, so again, this is non-singular. And again, in this case, you even have a generalized Fourier series representation. You can analyze it. And again, U2 is decaying in T, and therefore the solution in this case 2 is always tau periodic. So this is non-singular because the zeros of this determinants get closer to the black lines, but never get there. Now, this is not rigorous, it's numeric, it's only rigorous asymptotically, but we use two numerical ways of computing them for different values of beta. This is an older one, and this is a graph that Dave now has been producing, which is much more colorful. And I am not sure I completely understand how he does it, but in any case, the zeros are also here. That's for a higher value of beta. They should be closer to the lines, but they still never hit these lines. And we know, this is only finite, but asymptotically, we know that actually asymptotically, they will asymptote to the middle lines. So eventually they will move away from the green lines here. So they never coincide with the real roots. So again, the system that you obtain, which has this as determinant, is non-singular. You can solve it for the unknown conditions, then backtrack and prove that the solution is periodic. What is interesting is the case when beta is either plus or minus 1, because it's different, and it indicates that even when you look at Dirichlet or Neumann conditions, and in fact, even for the second order, you're not looking at the full picture of what can happen. So what happens in this case is that these are the determinants, and suddenly this determinant has real zeros. The zeros are on the real axis and on these other lines where the cube roots are. So there may be, depending on omega, depending on the period of the boundary condition, it's possible that you hit some of the zeros, in which case the system is singular. So either you have to expect that it's never the case that you hit one of the cube roots, or if you do, then the corresponding denominator is 0. In this case, it's just Gn 0. Okay, so assuming that the necessary condition, so you don't hit these cube roots, you can again construct U1 that's tau periodic. But then when you look at the solution U2 of the homogeneous version of this, so this is the you find that there is there are eigenvalues and eigenfunctions that form a complete basis. You can expand the solution U2 in terms of these eigenfunctions, and the eigenfunctions are just these exponentials in terms of these real zeros here. And these eigenfunctions individually, each one of them is periodic, but they each have a different period. And in fact, the periods are incommensurable. They're not rationally, they're not multiples, rational multiples. Only asymptotically that happens, but the distance between each of these zeros changes, varies with m. And so U2 in general is not periodic, it's just multi-oscillatory. And so in this case, U1 is periodic, but U2 is not periodic, it's not decaying, but the solution is not, cannot be periodic of the same period of the boundary condition or of any period. That we didn't expect. Again, this is a case that's always special, especially in every kind of way you might want to look at it. And it proves special also for this periodicity story. Okay, so in summary, if you have stayed with me throughout all this, there are essentially three possible cases. You can always split the solution in two. You always have one part that's tau periodic, and what is important is what happens to the homogeneous other part. And for free Schrodinger with Dirichlet boundary condition, for example, this other part is periodic always of period 2 over pi. So the condition is that there are necessary conditions that you require, but then if they are satisfied, the solution is only time periodic if the period of the boundary condition and 2 over pi are linearly dependent. Now, this is true for Dirichlet and Neumann boundary condition, and I speculate any such type of condition. But if there are Robin type boundary condition which displays the same oscillatory behavior for U2, maybe I mention it later. Okay, so this is specific to Dirichlet boundary condition, and for U2 decaying. We have seen you need no necessary condition. If U2 decays, U1 will drive what happens. Okay, so for the heat equation, for example, and also for Stokes with the uncoupled boundary condition or most coupled boundary condition, this is the case. And the solution is always asymptotically time periodic of the same period as the initial condition because U2 decays. But there are lots of cases when U2 is just, well, I write oscillatory, that could be periodic. I just mean that it's made of infinitely many different oscillations. Okay, and so in this case, the solution is not time periodic. I showed you an example, and that was the example of Stokes with this particular coupling parameter being plus or minus 1. But this is also the case for linear Schrodinger with some specific Robin boundary condition. So it is not a given, even in this linear problem, even when you have zero initial condition and only one datum driving periodicity, that the solution inherits this periodicity. It's a little bit, it's more varied than that, so it's more interesting. And that's it. This is the bibliography. We have written this up already, and it's been accepted. Not today, but not very long ago. And this is the previous work that I'm aware of. If any of you knows either a paper on this or any other experiment that requires time periodic boundary condition, I would be very happy to hear about it. Thank you.